Hello and welcome to the March 2017 Nutritionist webinar. I am Mary Ann Fessenden from Agricultural Modeling and Training Systems and serve as your English language host. These webinars provide access to technical seminars by internationally recognized speakers. The series presentations are held in English, Portuguese, and Spanish. Marcos Neves Pierre from Universidade Federal de Lavras will be hosting the Portuguese language presentation, with Marcelo Hans Ramos from 3R Lab facilitating. Paula Torillo from Argentina is hosting the Spanish language webinar. There will be a post-presentation question and answer period when listeners can submit questions through me, Marcos, or Paula. A complete recording of the archived webinars as well as the question and answer session for each will be available on the AMTS website. Very honored to have Dr. Larry Chase, Professor Emeritus, Cornell University, join us for the March Nutritionist webinar. Larry has been a professor at Cornell for nearly 40 years. A graduate of The Ohio State University, Larry went on to receive his master's from North Carolina State University and his PhD from Penn State University. Larry has been closely involved with the history of the development of the CNCPS with over 100 papers in publication. His current work has focused on management of ammonia and greenhouse gas emissions. Through his research, nutritionists have pushed the efficiency of nitrogen use on commercial dairy farms. In addition to his research, during his tenure at Cornell, Larry was primarily responsible for outreach and extension in support of the CNCPS model. Larry and his wife Arlene live in Ithaca. Please join me in welcoming Larry Chase to the Nutritionist as he presents on cows, gases, and the environment.
Okay. Thank you very much for AMTS and the other sponsors for inviting me to participate in the program. And the introduction by Mary Ann was probably more than we needed. But what we want to do today is talk a little bit about cows, gases, and the environment, which is maybe a topic that you don't talk about all that often. And in terms of acknowledgments, I'd also like to indicate that some of this information is part of a sustainable dairy project funded by USDA, which is a large project, multi-state, with about 50 scientists looking at the effect of climate change and greenhouse gases. And so I'm one of the 3 people from Cornell involved in that project. So have you thought about the modern dairy cow as a biological manufacturing facility? Really, if we think about the modern dairy cow, it's really quite interesting to think about all the dynamics that happen in this animal, in the ruminant animals, that can convert a wide range of feeds of varying qualities into high-quality protein products for human consumption. And one of the questions that always is interesting to think about is, what are the limits to milk production in a dairy cow? And it seems like every time we think we have the answer, then some cow comes along and changes the answer. And just recently, the answer was changed again. There was a cow in the herd in Wisconsin, a 4-year-old cow in 365-day lactation, produced over 77,000 pounds of milk. That's over 35,000 kilograms. For every day she was milked, she averaged 212 pounds per day, or 96 kilograms of milk per day, every day for 365 days. That is really a marvel of biological manufacturing plant. And this cow happens to be housed in a herd of about 94 cows, and the herd average is over 44,000 pounds of milk, or over 20,000 kilograms. So it's just not one cow in this herd, it's the whole herd is a very high production situation. And if you think about lifetime production, this is one cow, and there's been another one since has done more than this. This cow produced over 200,000 kilograms of milk in the lifetime, and for every day she was milked throughout her whole life, she averaged 42 kilograms of milk per day. Just an amazing feat of biology and that rumen fermentation system that we work with. So basically, if we think about the cow as a manufacturing plant, the inputs are feed and water, outputs are milk and meat, and the co-products, which we're going to be talking about today, manure, heat, and gases. So why are we concerned about gas emissions in dairy cows? To me, the primary reason is that gas emissions from the animal represent a loss of consumed nutrients that go to the environment instead of going to milk production. The energy and protein lost in producing gas means we can't use that energy and protein to make milk, and so we lose production, and we lose the efficiency, and we lose profitability. The secondary reason, which some people think is the primary, but I think it's secondary, is environmental. There's increasing government regulations on agriculture to lower emissions to the environment. Currently in the United States, the dairy industry is being regulated on nitrogen and phosphorus on our large dairy herds, but ammonia and methane regulations are probably the next targets for the dairy industry. So if we look at the ammonia emissions in the U.S., according to the United States Environmental Protection Agency, cattle are the primary source at about 45% of the total ammonia emissions in the United States. If we look at a total dairy farm, and we look basically, we're staying today with the barn primarily. In the barn, we have three emissions that we have to be concerned about: ammonia, methane, and particulate matter. So we're going to address the ammonia and the methane parts today in this presentation. The other thing to think about is how efficient are these cows at converting the nitrogen consumed into nitrogen in the milk. And this is just a schematic that shows as we go from 60 pounds of milk to 120 pounds of milk, the efficiency of conversion goes up. That means the grams of nitrogen consumed, the percent of those that end up in the milk, are higher in the high-producing cow. But you can see even in these high-producing cows, we're only still getting about 35 to 40% of the consumed nitrogen captured in the milk. The rest of that obviously then is going out into the manure and ammonia into the environment. Okay. So on this slide, I think it's probably one of the most important slides in the presentation. It was put together by Dr. Mary Beth Hall when she was at the University of Florida. And it's a schematic really of how nitrogen protein is used in the rumen. And you can see that as feed crude protein or nitrogen enters the rumen, there are two things that happen to that. One, some of it is converted to ammonia. A second part is what we call escape or bypass protein. If we look at in this schematic, the three things that are really important: ammonia, carbohydrates, and rumen microorganisms. Ammonia, carbohydrates, and microbes are really the key not only to the efficiency of use in the dairy cow, but the profitability. So the nitrogen enters and gets converted to ammonia. It has two options. It can be converted to microbial protein from the energy in the rumen available carbohydrates, or if there's an imbalance between ammonia and carbohydrates, the excess ammonia goes to the liver, gets converted to urea, and is excreted from the cow as urinary nitrogen or milk nitrogen. Some of it can be recycled also. But again, this is that balance of ammonia and carbohydrates in the rumen that determines, number one, how many rumen microbes we're able to grow and how efficient we are in using the feed nitrogen and minimizing the amount going out into the urine or into the milk. Just think about it this way. Everybody talks about protein, and protein's important, but Dr. Chuck Schwab put this together a few years ago, and I think it's very important to say that the big driver, really, of microbial protein production in the rumen is the fermentable carbohydrates. They are the driver that help take the fermentable carbohydrates, the degradable protein or the ammonia, and convert that to microbial protein. We have to have those two systems meshed together if we're going to optimize that efficiency of the animal. In this chart is one that Dr. Mike Van Amberg put together. It's a combination of both research data and commercial farm ration data. And we'd like to talk through this because I think it brings up a concept that we have to be thinking about. So on this, he has varying levels of nitrogen intake from about a little over 500 grams a day up to almost 750 grams per day. So what happens in these cows and these data sets that Mike looked at to the various sources of nitrogen and excretions? Well, if we look at the fecal nitrogen, the red, it's constant. It really doesn't change very much at all. Relatively small change in that. So basically it says no matter what nitrogen intake, the grams of fecal nitrogen are relatively constant in the dairy cow. If we look at the blue line, the milk nitrogen, again, relatively constant. Now, I need to clarify what this line is. This is the grams of nitrogen in the milk excreted per day. Not the percent nitrogen, but the total grams. And again, what that indicates to us is that in this data set, there was really no differences in milk production as we went across that spectrum of nitrogen intakes. So the total grams of nitrogen excreted in the milk were relatively constant. The only thing that really changed in this data set as nitrogen intake increased was urinary nitrogen. And you see that's almost a linear response. That as we feed more nitrogen and we don't have more in the milk or the feces, the rest of it gets excreted through the urine. What we want to find is the balance point where we're maximizing our milk, minimizing the urinary fecal nitrogen. We're going to look at a data set from Dr. Glenn Broderick at the U.S. Dairy Forage Research Center, which again I think helps us understand the basis for nitrogen use, urea excretion, and ammonia. So in this particular project, Dr. Broderick had rations varying from 13.5 to 19.4% protein. As you would expect, the nitrogen intake, the red bars, as the rations had higher levels of total crude protein, nitrogen intake went up, which makes sense because you have a ration with higher nitrogen, so they're consuming more grams per day of nitrogen. If you look at manure nitrogen, the green, it also tends to go up. Now that's total manure nitrogen, both urine and feces. So in Glenn's study, as we increased intake of ration protein was higher, we had more nitrogen both consumed and excreted by the cow. But let's look at the partition of those excretions. If we look at milk, which is the gray bar, you'll see in this project, there was very little difference in milk. Basically, it says milk production was basically very similar for all 5 levels of ration crude protein. Fecal, the green, again was fairly constant. It changed a little bit, but not a lot, as we went from the lower protein ration to the higher protein ration. Again, the red, the urinary, that's the one that just keeps increasing. Every time you add a higher protein ration, you get higher levels of your urinary urea nitrogen, which again is a waste in terms of lowering efficiency. So the question then, how can we relate this to ammonia? So I did a calculation using the grams of urinary nitrogen per day, and said that 65% of that, which is drawn from literature data, is converted to ammonia. Now, it's not, in honesty, it's not a constant factor. It varies a little bit with intake, but 65% is a good ballpark to use as a starting point. And if we do that, then you can see the ammonia emissions on Glenn's rations went from a little over 60 grams per cow per day to up to over 160 grams per cow per day. Basically monitoring very closely to urinary nitrogen excretion. And so we can get a prediction of ammonia emissions by looking at the urinary nitrogen excretion in the cow. Also, the milk nitrogen efficiency, or the percent of the nitrogen consumed by the cow that was captured in the milk, this is Glenn's study still, went down as we went to the higher protein rations because we had more excretion of nitrogen in the manure and in the urine. So I think this shows the concept here that we're working with on what we want to do to improve efficiency of use of nitrogen, lower excretion, and decrease the ammonia. There was a study at the University of California, Davis, one of the students there, and they directly measured the relationship of ration crude protein in the grams of ammonia per cow per day. In this project, they had rations from 15 to 21% protein, and you can see the similar pattern to what we saw in Dr. Broderick's study. As ration protein went up, the grams of nitrogen, ammonia and nitrogen in grams per day went up from about 60 at the 15% protein ration to about 90 at the 17% protein ration. So even though we only had a small change in protein, 15 to 17, we had a large change in ammonia, which says that extra protein in the ration was not being used very effectively or efficiently in terms of milk production. So what can we do to reduce, and how much can we reduce ammonia? If you look at a trial that was done with growing dairy heifers, they looked at two levels of protein in the total mixed ration, 15 and 17.4% crude protein. Nitrogen intake was 14% lower on the 15% ration. Excretion was 13% lower, so basically it said any extra nitrogen was excreted. But the more important thing, if you went from the 17.4 to the 15, ammonia emissions were reduced by 28%. So intake was reduced 14%, excretion reduced 13%, and ammonia 28% by going from 17.4 to 15% protein. So that's pretty impressive that we can get that much change. What about a dairy cow? Well, if we go back to Glenn Broderick's study, if in his study, when you lowered the ration protein from 16.5 to 15%, ammonia emissions went down 20%. If we look at the study from California, lowering protein from 17 to 15%, ammonia emissions went down 37%. So you can see that with very small ration adjustments, we have the opportunity to make very large changes in ammonia emissions. And remember, all the ammonia emissions are representing inefficiency of nitrogen use and loss of potential milk production. So how do we decrease it at the dairy farm? And go back to think about Mary Beth's slide, looking at the balance of ammonia and rumen available carbohydrates. We may be able to shift some of the rumen degradable protein into rumen undegradable protein sources. So shift a little bit of a highly degradable protein source for one that's less degradable. That may help decrease ammonia. Increase the fermentable carbohydrates to make sure we can use as much of the ammonia in the rumen as possible. But obviously we know there's a limit to how much fermentable carbohydrate we can have before we upset the acid-base balance and the pH in the rumen. Select degradable protein sources that have lower rates of breakdown. So the ammonia is available slower at a more uniform rate, which increases the chance that it may be captured with fermentable carbohydrates and converted to microbial protein. Try to match the rates of digestion of the protein and carbohydrate sources. If you have a protein source rapidly available and a carbohydrate source that's slowly available, then you have a mismatch, and that ammonia won't be able to be captured by that carbohydrate source. And then the other one that helps us practically in ration formulation is use multiple sources of protein and carbohydrate ingredients, and that gives us a more uniform pattern of ammonia release and available carbohydrates available in the rumen. So these are sort of the general approaches we can take to maximize that rumen efficiency, minimize the ammonia spillover, and maximize our microbial protein production. And basically, this is a chart that was put in the Journal of Animal Science in 1976 by Dr. Ron Johnson from Oklahoma State University. And it sort of shows the goal that we're after. If we look at the ammonia level, it changes a little bit, not a lot, this is a 24-hour period. That's what we want, sort of a slow, more constant level. And note that in this case, this is schematic again. The carbohydrate fermentation, you have a rapid portion of the carbohydrates, you have some rapid protein, you have a slower carbohydrate with some slower protein, and you have some even slower carbohydrate, even slower protein. By matching those, that's how you get a more constant rumen ammonia level. So if we have a lot of carbohydrate and not much ammonia, then we're going to have excess carbohydrate and a chance for a pH problem. If we have too much ammonia, not enough carbohydrate, then we're going to have a lot of excess ammonia. So again, keep this schematic in mind, because that's sort of the goal you're working with, is this fermentation system to match the rates of availability of ammonia and fermentable carbohydrate to maximize microbial protein synthesis and minimize ammonia excretion to the environment. Feeding management also plays a big role in this. In herds that feed grain separately from forage, you should feed a carbohydrate energy source before the animal gets the protein feed, so that when the protein is released and the ammonia becomes available, the carbohydrate's already there and ready to utilize that ammonia. We also want to minimize what we call slug feeding, or cows eating extremely large meals. And we want to use feeding management practices that encourage cows to eat more frequently and have smaller meals. So if we can get the same amount of dry matter intake in 10 meals a day versus 5 meals a day, we have a chance for more uniform rumen fermentation, more use of that nitrogen, and less nitrogen going to the environment via the ammonia. So how do we monitor this on a dairy farm? Because then that becomes one of the key points that all of us have to work with, and many of you will have to work with as these regulations come along. Unfortunately, there's not a way we can directly measure it very easily at the farm. So we have to use indirect measures. One option is to use urinary nitrogen excretion. And because, as we showed earlier, some of the urinary nitrogen is converted to ammonia. And this varies due to factors. It's not a constant number, but as a starting point in the CNCPS model, we use a value of 65%. So if you had 100 grams of urinary nitrogen, we would think that's about 65 grams of ammonia. Urinary nitrogen excretion is on a number of reports in the AMTS system. So you can easily get an ammonia value by looking at your reports and looking at the urinary nitrogen grams per day, making that conversion. Another thing to look at on your reports is the rumen ammonia balance. If we can keep that between 110 and 150% of requirements, that'll be another index that we're doing a pretty decent job in maximizing the efficiency of that rumen fermentation. So those are a couple things in your reports that you can look at to get an index. Another tool that's available on many farms is the use of milk urea nitrogen. At least many of our dairies in the U.S., our dairymen routinely get this number on every load of milk shipped by the milk plant. So it's actually a value that comes to the dairy farm. They don't really have to pay for it directly, but it gives them a monitor. And for herds that are on milk testing programs, they have an option to get this on every individual cow. So the question really is, how is this related? And how well is it related to ammonia? Well, if we go back to the data from the University of California, Davis, and now we look at the relationship of ration crude protein and milk urea nitrogen in milligrams per 100 or deciliter, you'll see the same pattern between ration crude protein and the previous slide, which had ration protein and ammonia. Essentially the same pattern, which says they sort of track together, which makes sense. That if you have more ammonia excreted, you should have a higher level of milk urea nitrogen. Some work that Dr. Pekka Huhtinen did in Finland looked at data from a bunch of studies, and they looked at the relationship between rumen ammonia and milk urea. And you can see that it was highly correlated with a R square of about 0.93. So it's a pretty linear trend between rumen ammonia level, in this case, and milk urea nitrogen. So again, we can measure milk urea nitrogen at the farm. We can't measure rumen ammonia very well. So it says that, again, it's a very good index that we can use. So what are the guidelines? The guidelines we use in our New York Precision Feed Management Program, we want the MUN values in herds to be between 8 and 12 milligrams per deciliter. Values greater than 12 give us an index of inefficiency of nitrogen use and an opportunity to readjust rations and improve nitrogen efficiency. We have many high-producing herds in New York, over excess of 14,000 kilos per cow, that have MUN values of 7 to 9 with high levels of reproductive efficiency. If we get MUN values much less than 5 or 6, it may indicate a shortage of ammonia in the rumen, and we could be limiting both microbial protein synthesis and milk production. So I think this is a nice tool that we can use to get sort of an index of how we're doing in that nitrogen efficiency use within the animal. So these cows are probably wondering, what's all this mean and what's coming up next? Well, what's coming next is we're going to shift over to methane. And this is on a magazine cover a number of years ago. It says cows produce 20% of all U.S. methane emissions. Now, again, we don't know where that number came from, and we're going to show you some values here in a minute to say that that 20% isn't very valid. Let's see. Oops, go back one. And you also may have seen a picture like this. Again, false. Over 90% of the methane emitted by the cow comes out of the mouth, not from the back end. But again, people show this to try to say these cows are terrible for the environment with the methane released. So basically, if we think about it, as we convert feed to animal product, what we want to do is get milk. Anytime we get methane, heat, and feces and urine, we're losing on our feed conversion efficiency. And this is some data that was put together by the people at University of Reading. And basically says as intake goes up in a dairy cow, primary intake goes up, the methane as percent of gross energy intake tends to go down. But still, you're looking at only maybe 7% here to maybe low of 3 or 4% over here. So, you know, our dairy cows may be losing 3, 6, 8% of the gross energy intake in methane, and any loss there means that energy is not available for milk production. So what's the situation with the greenhouse gases? This is the most recent data from U.S. Environmental Protection Agency, and it shows that between 1990 and 2014, the CO2, carbon dioxide emissions went from 5,100 million metric tons to 5,500 million metric tons. So there was an increase in CO2 over that period of time. If we look at the next bar, the methane, it actually decreased from 774 to 731. So at least in the U.S., over this period of time, methane production, total emissions have gone down slightly. And the second one, the next one is nitrous oxide. And again, that's been relatively constant, 406, 403. So the big change in greenhouse gas emissions in the U.S. anyhow, over this period of time, has been carbon dioxide, not methane or nitrous oxide. If we look at the methane emissions, CH4 methane, the total, like we said, went down. Enteric, that's from ruminants, basically didn't change. It stayed about the same over this 14-year period of time. That doesn't mean that we're not part of the problem. We are a piece of the puzzle. But again, we've not been increasing as the total greenhouse gases have gone up. Methane represents about 11% of the total greenhouse gas emissions in the United States. And where does that methane come from? Well, we said enteric emissions from ruminants are about 22% of the total methane. Enteric from ruminants are 2.4% of total U.S. greenhouse gas emissions. That's from all ruminants. The methane emissions from dairy cows are about 5.7% of total methane emissions, which basically says the current situation in the United States is methane emissions from dairy cows account for about 0.6% of all the U.S. greenhouse gas emissions, not the 20% that was on that chart. So even though we're only 0.6%, there's still reasons we want to change that. And again, the primary one is anything we can do to reduce methane makes more feed energy available for milk synthesis. Keep flip-flopping. Here we go. Now we got it. So we're just going to use one chart, one slide here to sort of say, where does methane come from in the rumen? Basically what happens, how is methane produced in the rumen? You basically get CO2 is reduced when you have hydrogen. CO2 is reduced to methane. So where does this come from? Well, the VFAs like acetate and butyrate, they provide a hydrogen source in the rumen. Microbial growth from amino acids is a hydrogen source. So those three add hydrogen into the rumen. Fermentation that produces propionate, like from starches and carbohydrates and valerate, tend to be sinks. They soak up hydrogen. Microbial growth of ammonia soaks up hydrogen. When we use lipids and biohydrogenate fats in the rumen, they soak up. They're a sink for hydrogen. And so really what happens in the rumen, it's a balance of how much hydrogen source do you have versus how much sink. The more we have that we can use in the sinks in the rumen and reduce the excess, then there's less hydrogen to interact with carbon dioxide to be converted to methane. So again, we're back to how do we maximize and adjust that rumen fermentation so we minimize the amount of hydrogen available to be converted to methane in that rumen situation. There is a debate of how you report this and measure it. And to take a look at this, we use the Cornell model, version 6.5, with just a typical ration, forage of grain, a little heavier corn size to alfalfa, and you can see the combinations there of about 17% protein, 26% starch. And we just said at different levels of milk production, how much methane would we get from these rations? So we're going from 40 to 120 pounds of milk, or 18 to 54 kilograms. The grams per day go from 373 to 509. Well, that makes sense. As cows produce more milk, they have to eat more feed. If they eat more feed, they have a more active rumen, and so there'll be more total activity in the rumen. So it makes sense that the methane per total grams per day would go up because of feed consumption. However, if you look at the methane emissions in grams per pound of milk produced, or grams per kilogram, they go down, which says that we're more efficient there. The higher producing cow excretes less methane per unit of milk. So we're gaining efficiency there. So currently, in most of the scientific literature that you read, when they look at carbon footprint, they're reporting methane emissions per unit of product, per unit of milk. And so in this case, you can see the higher producing cows are much more beneficial to us in providing that efficiency or lower methane per unit of milk. The thing we have to think about is we adjust rations. Everybody's interested in adjusting rations for the cows, but a dairy herd has milking cows, heifers, and dry cows. What percent of the methane comes from the milking cows? This is just 3 herds that we have data on. We had data for all the animal groups, ran them through our model, and predicted the methane emissions. And the AMTS model predicts methane in liters per day. I usually predict grams per day, but either one works fine. But again, you can see that the milk cows are about 70-75% of the total. Dry cows are about 7 or 8%. The heifers 18 or 20%. So as we adjust the cow rations, and you say, what's going to mean to the total herd? Remember, any adjustment you make on the cows is diluted down a little bit on the effect for the whole herd because of the other animal groups. What are some of the relationships? As part of the large climate change project, we're doing a lot of computer modeling of rations for cows and looking at what ration components are related to methane production. And so as part of that, we developed a database of 199 rations from basically 199 dairy herds, you might say, all run through the CNCPS 6.5 program. Average milk production was 84 pounds with a range of 50 to 128. Average intake, 51 pounds with a range of 35 to 70. So a fairly wide range of milk and intake in these commercial dairy herds. We're just going to look at a couple of simple correlations. The correlation, the relationship between dry matter intake and methane emissions grams per day was positive 0.795. So that says basically as cows eat more feed, they produce more methane in grams per day. And actually, I was reading a paper the other day. This was reported in 1930 by Dr. Chris, that he found the same relationship. So again, some of this information we come up with now, if you go back to the literature, a lot of it sits there. On the other hand, if you look at the correlation between increase in intake and methane emissions grams per pound of milk, not grams per day, grams per pound, it's a negative 0.65. So it sort of fits with that previous chart. So as we increase intake, yes, we get more total grams per day, we get less grams per unit of milk because of an efficiency difference. we decrease methane emissions in a dairy herd? Well, there's a large number of things and a lot of review papers out here. But if we try to come down to some of the more simple concepts, number one, if we can increase milk per cow, we will decrease methane per unit of milk produced. We saw that earlier. If we decrease cow numbers, then we reduce methane. That's not a very popular item with most of our dairymen, but that would be a way to decrease it. Anything we do to improve feed efficiency, more milk per unit of dry matter intake lowers methane emissions, both in grams and in grams per pound of milk. And the other big one that we don't think about sometimes is to decrease the number of non-productive days. Shorter dry periods, better reproductive performance, and heifers calving at an earlier age at first calving. All of those are non-productive days that contribute methane emissions, but there's no product to counterbalance them with. Some examples of management practices that we can use that can have an effect on methane emissions. Milking frequency. If we milk 3 times a day versus twice, we usually get 6, 8, 9% more milk. So that means that we're going to get more milk per unit and less methane per gram of milk produced. We talked about reproductive efficiency, and we'll show you a couple of examples of that in a minute. The use of bovine somatotropin, again, improves milk production, but also improves feed efficiency conversion. We know that's a controversial topic. Some countries can't use it. Some co-ops in the United States don't let us use it, but it is a tool that potentially could help. Uniform grouping of animals, so we can better tighten the ration and less variability of the ration and the animals in that group. If you have a group of animals where they range in milk production from, say, 40 pounds to 150 pounds, and the other person has a group where they range in milk from 80 pounds to 120, there's a difference in uniformity of the group and how tight we can make the ration. And by making the ration tighter and the grouping better, we can improve the efficiency of conversion of feed to milk and lower the excretion of methane. Healthy animals, transition cow management, potential use of ionophores, more accurate ration formulation, mixing, and delivery. On many of our herds, this is an opportunity area. Sometimes the formulation, the ration you formulate with AMTS is excellent, but it doesn't get transferred to the cows very well. And so a lot of times we can make really a lot of improvement there with better mixing delivery of that ration. Forage quality we'll talk about in a minute, and reduced age at first calving, we'll show an example of that. These are just some management tools, not nutrition, management tools we can use to alter and change methane emissions on the dairy farm. So what's a maximum? How much can we reduce it? Well, Joanne Knapp had a paper in Dairy Science in 2014, and it was sort of a literature review and looked at the data and taking the research data and looking at it. What was the maximums? And in this paper, they suggested that genetic selection may have the potential to lower methane units per unit of energy-corrected milk by 18%, feeding and nutrition about 15%. Some of the rumen modifiers, we'll give an example later, about 5%. Other management strategies, some of the things we talked about, fertility, age at first calving, 18%. And then if you add them all together, she said it's probably about 30% because they're assumed not to be totally additive. There's some counterbalance. So again, we have an option with feeding nutrition, maybe 15% to lower those methane in the herds. She also made a chart and said, let's look at the impact of just a few things. For example, we talked about increasing dry matter intake. If we increase dry matter intake about 2.2 pounds or 1 kilogram, methane is reduced about 2 to 6% per unit of milk produced. Changing forage particle size didn't have much impact on methane emissions. Processing grain so that we improve total tract starch digestibility. If we can improve total tract starch digestibility, say 5%, we get a decrease of about 1 to 2.5% of methane emissions per unit of milk produced. Rumen pH, this is the big one. If we lower rumen pH to less than 5.5, we can lower methane emissions 15 to 20%. But I think all of you recognize that's a very unhealthy cow. So even though it theoretically works, it's not something we probably want to do. And feeding additional grain, as we increase the non-fiber carbohydrates, primarily starch, if we increase a 1% increase in non-fiber carbohydrates, we get about a 2% decrease in methane per unit of milk produced. So there's some simple things we can do to help change that methane emissions on the dairy herds. Oops. Let's talk about the productivity for a minute that we chatted about. There was a paper in 2011 that said a 1 standard deviation increase in feed efficiency could lower CO2 equivalents. This is all methane by 6.5%. And we said earlier BST has the potential to lower methane about 8% per unit of milk produced. Forages, the higher quality forages produce less methane per unit of forage consumed versus lower quality forages. So a basic concept of ruminant dairy cattle nutrition is always using higher quality forages for higher producing cows. That also helps us lower the emissions per unit of milk produced. There is some work out there indicating that if we replace some of the grass or legume forages with corn silage, that this can help to lower methane emissions because we're getting more starch, more propionate, and less acetate in the rumen. Remember that sink of hydrogen positive and hydrogen negative? However, when we get to a real farm, what we have to think about is, on this farm, what is the best forage to produce based on the farm's agronomy and environmental considerations? We may say that a high corn silage ration is a good for reducing methane, but if that doesn't fit the farm's soil, environmental resources, that's not a good answer on that farm. So I think the first step, select the forages based on the soil, climate, environmental situation, and then within that, produce the highest quality forage of that particular forage. Yes, if we had more corn silage, it would help, but that doesn't fit all farms. So if we could make a higher quality grass forage instead of a lower quality grass forage, that would help us lower methane emissions per unit of milk produced. Dr. Bill Weiss at Ohio State said, if we reduce age at first calving by 2 months, that lowers methane in the whole herd by about 1.5%. It doesn't seem much, but if you have 1% from this and a couple percent from something else, then eventually you get up to a number that's fairly significant. He also said if we can reduce the culling rate, the turnover rate in the herd by 5 units, that can lower methane in the herd by about 3%. So you see that if we went to a herd and we could change age at first calving and have less cow turnover, maybe we could change methane 4 or 5% with those simple management practices without worrying about the nutrition. Phil Garnsworthy in England put together a paper a number of years ago and said, what's the effect of reproductive efficiency on both methane and ammonia production in herds in the United Kingdom? So he basically compared the pregnancy rate of 19% at that time versus what they had in 1995, which was 25%. And then he looked at 2 levels of milk production, 13,500 and 20,000 pounds of milk, and said, what is the impact of these changes in milk production and pregnancy rate on emissions. If we can get a higher pregnancy rate, if we can just go from the 19 back to the 25, methane would be reduced 4 to 11% per 100 cows. Ammonia, 4 to 9% per 100 cows. So again, these are things related to, these are non-nutritional factors that can end up having a significant impact on our emissions of both methane and ammonia at the farm level. There was an interesting paper presented by Dr. Alex Christoff from Penn State University at the Dairy Science meeting in 2015. There's a lot of interest in various rumen modifiers that we could add something to the rumen that would change that population, microbial fermentation, and maybe decrease methane emissions. The reason we show this one is this is the only one I've seen so far where it's actually been done in a long-term trial, 12 weeks. There's been a lot of in vitro work where you put in different compounds and they can drop methane 30, 40, up to 80%. But nobody has really said in an animal over a long time, does this effect stay constant or do the rumen bugs adapt? So in this study that Dr. Alex did, over 12 weeks, the average production of these cows is about 45 kilograms a day or 100 pounds of milk. They use 0, 40, 60, or 80 milligrams per kilogram feed of 3-nitrooxypropanol. Methane emissions were reduced 25 to 30%. That's over a 12-week period. So it looks like this one potentially can work long term. Now, it's going to be a long time before something like this would be available on the market because we'd have to go through a lot of additional trials and regulatory approaches to get through our Food and Drug Administration. But it says there's potential for some of these rumen modifiers to have a long-term effect, which might be very significant in terms of the amount of methane they might be able to reduce. Economics also is one that we have to think about. A couple of recent papers from California have indicated that at times adjusting rations to lower methane emissions may increase feed costs and lower profitability. Other times it's going to lower feed cost and improve profitability. It's all a matter of feed price and milk price. So in most cases that we've run so far, that we've looked at with our feed and milk prices, generally if we reduce methane emissions, we're lowering feed cost and improving profitability. But if you get a unique set of prices of feed and milk, it could go the other way. So this is one we have to think about and take a look at as we move ahead, because we have to also maintain profitability of farms as we do this manipulations to change methane. So I'm going to give you the last slide here. If you want to go home tomorrow and really lower methane emissions in a dairy herd, if you follow this slide, you will be able to do it dramatically. Feed high corn silage rations, feed high starch rations, feed high levels of unsaturated fatty acids, feed high levels of added nitrates, and feed the 3-NOP that Dr. Christoff worked with. If you do that, you can probably reduce methane emissions 70, 80, 90%. Now, anybody see a problem with that? You also may have lower intake, lower milk, and dead cows. But it would lower methane really fast. Okay? So again, we have to think about the counterbalances as we go through this. So we're going to try to wrap it up now and do a quick summary, and then I guess you'll have some questions. I look at it both long-term and short-term. Long-term, over the next 5, 10, 15 years. Genetics. Genetics can help us to improve feed efficiency. The challenge on genetics right now is we don't have a big enough database of measured feed efficiency values yet to take advantage of it. But over the next 5, 10, 15 years, that could be a part that comes in to help us improve our efficiency and reduce our emissions to the environment. There are people talking about alterations of rumen microbial population. Again, that, if it ever happens to be long-term, because there is some good work out of Wisconsin showing that if you change things dramatically in the rumen, it only takes the bugs 3 to 5 weeks to change back to where they were. They seem to adapt pretty quickly. Added compounds, we talked about the example from Dr. Christoph. I think those are a few years away because, number one, they need more animal trials, larger numbers, longer term. And secondly, through the get regulatory approval process, it's a long-term and expensive process. And then altering herd management. You know, if we change reproduction of herd, it's going to take us a year or two. Or if we change our heifer program to have animals calve earlier, that takes, 1, 2, 3 years to get that whole cycle taken together. So these are all things that can help us. I think they're a little bit long-term, but they should also be thought about. Shorter term, some of the things that you've talked about with your clients and as you work forever. Improve the efficiency of feed use. That lowers methane per unit of milk. Use fiber and starch digestibility values when you balance rations, so we can do a better job of balancing the ration and a more effective and efficient rumen fermentation. Utilize feed additives and production technologies based on research data. And again, that helps us make those rations more fine-tuned and a better balance in that rumen fermentation. And forage type and quality. For example, corn silage may be a better fit, but it doesn't fit all farms. But forage quality definitely showing that high-quality forages have less methane per unit of forage consumed. And then provide feeding management systems that improve cow comfort, herd health, and reproductive performance. Anytime you have a cow that's under stress or not healthy, you're going to have more opportunity for imbalances and lower efficiency of feed use. And precision feeding, consistency of feed mixing, delivery, and feed bunk management. I think those are ones that on many of our herds are really opportunity areas that we haven't tapped into yet as well as we could. So at this point, I want to say thank you for your attention. This is our new Cornell Dairy Research Center, which we opened in 2013. We're milking about 600 cows, and we're about 45 kilos of milk per day. So at this time, thank you, and I guess we'll see what questions we have.
Thank you, Larry. First of all, I want to invite you all to join us next month for Dr. Mark Hannigan, professor at Virginia Tech, where his projects include work to improve amino acid and ruminally degraded protein requirement equations, improve the predictions of volatile fatty acids and methane production, develop genomic selection tools for feed efficiency, and to evaluate the role of ruminants in human food system. Mark will discuss whether there is really a single limiting amino acid. His talk will also include financial considerations for ration formulation. Please note that the date and the time for the April webinar are different than is normal. In an effort to be at a more agreeable time for our participants in Europe and South Africa, we'll hold the webinar at midday your time, or our time. Additionally, the webinar had to be moved to the first Wednesday of the month due to travel complications. So please join us at 1 p.m. Eastern Daylight Time on April 5th. I also want to mention a webinar that AMTS will be holding on March 21st at 1 p.m. Eastern Daylight Time, specifically for anyone involved in feed animal nutrition and care in the United States. Dr. Melanie Hemingway, the NICE CHAP coordinator, will speak on the Veterinary Feed Directive. Check the website or email me for more details. I'd like to thank our sponsors and the people that make this possible: Tom Taluki and AMTS USA and Global, Marcos Neves Pereira, University of Lavras, Marcos Hens Ramos at 3R Lab in Brazil, Paula Torillo in Argentina, and our translators at each location. We have generous sponsors that make it possible for us to get great speakers and manage the program. We thank our gold sponsor, Ajinomoto Heartland, Superior Nutrition through Amino Acids, Our silver sponsors this year are Arm & Hammer Animal Nutrition, R&D Life Sciences, Vertus, makers of Strata with EPA, DHA omega-3s, and Prequil with omega-6s, Cumberland Valley Analytical Services, Dairy One Forage Laboratory, and Dairyland Laboratories. Our bronze sponsors are Jeffo, Life Made Easier, Adiseo, AminoMax, and QLF. So with that, I will start to take questions in the question and answer window. If you'll type them in, I can read the questions. We'll see if we have some questions from Argentina and from Brazil. Hi, Marcos. Do you have any questions?
Yes, we do, Marian. Dr. Chase, thanks for the talk. And there is an interesting question about meal values in milk here. You're currently recommending like about 9 to 12 milligrams per deciliter, as you said. And the question is, if you look at the surveys of diets in the United States, the average crude protein level of the diet is still high, like at least some surveys we have seen published. And the meal are much lower than, let's say, we would have like 15, 20 years ago. What do you think is going on? Like probably dilution because cows are making more milk, so that's why meal are going down, or the goal for meal is much lower today, or you think like you're doing a better job in formulating diets, but the surveys don't support it. And so the idea is, for example, to evaluate diets, to evaluate nitrogen balance in the rumen. Shouldn't it be better to think about like the flux of ammonia in milligrams per day and not milligrams per liter as we are doing? Like could our high-producing cows be diluting ammonia in milk?
Okay, good question, because we get these all the time. I see the same surveys that you see, and I'm not sure exactly where all the data comes from. I can tell you that in New York, over the last 10, 15 years, our herds are feeding much lower levels of protein than they were 10 or 15 years ago. And we have a fair number of herds right now feeding 15, 16% protein, one herd of 14. And our MUN levels have gone down also. And I think it's, as you know and I know, crude protein is not that good of a measure. It's really metabolizable protein is what we should be using, but our industry and our dairymen haven't caught up with that yet. So I think basically what I see, yes, I think we are doing a better job of formulation. We do have the higher producing cow, and I think we are getting better nitrogen efficiency of use, and I think that's why we tend to see lower urea and nitrogen levels now than we did a few years ago. But we do run into those herds, as you indicated, that are high protein feeding, and they will have high levels of milk urea nitrogen normally. Does that help?
Yeah, I think that's good. Okay, thank you.
Marcos, if you have another question, you could go ahead and ask it if you'd like.
Yeah, there's another one. There's the last one, I think. Then I go to the Brazilian seminar.
Okay,
someone was asking about if you know that about on the use of tannins to reduce the ammonia emissions in manure, like feeding the cow with tannin to reduce nitrogen loss in legumes and manure loss.
Mm-hmm. So, I mean, you wonder if there's compounds we can add to reduce ammonia loss in manure? Yeah.
Specifically tannins, you know about anything in the literature on tannin feeding? Would that go?
I'm not that familiar with it, but I know that there are people working on that. Yes, one of the way we're working with it in our project, I guess the large project is the more we can reduce going into the manure, that helps us a lot. And then they're looking at all kinds of alternative treatments and covers and storage mechanisms to further reduce ammonia emissions. So I think there are things we can do at the manure level. I'm not that familiar with all the techniques that are there, but I think there are some. A very simple one is to make the environment a little acidic, and that'll help also.
Okay, so someone is asking here also if the yeast feeding can reduce emission of gases by dairy cows.
What?
Live yeast or dead yeast products?
Well, probably. Okay, if you think about yeast, the way that yeast would work, and I've not seen any real trials looking at yeast and emissions, but if yeast helps improve the overall efficiency of rumen fermentation, then that should have an opportunity to lower emissions. So it would be sort of a indirect by improving the efficiency of fermentation in the rumen, and as a result of that, then you might get some reduction of the emissions. That's the way I would visualize it anyhow, but I haven't seen any direct trials.
Okay, thank you. Go ahead, Marion.
Okay, and Marcos, thank you for joining us. Am I going to assume that you'll be leaving us now?
Okay, thank you.
Okay.
Bye,
Thanks.
everybody. Good night.
Bye, Marcos. Larry, I have some questions from Paula Torillo in Argentina. I'm going to let her go ahead. Paula is, she'll type to me and let me know. Larry, I have a question. Let's see. So in light of the reduced age at first calving and reproductive efficiencies, how have there been any studies that have compared sort of maybe jerseys and how they might compare in their methane emissions or control there?
Let's see. There's been a little bit of work, but not very much. The problem with jerseys is there's very few jerseys in research herds, unfortunately. 20 years ago, almost every university had a herd of jerseys and Holsteins. Now there's very few jerseys out there. So we do have on another project I'm working on. We do have one of the highest producing Jersey herds in the United States on the project, and we are running their herds through AMTS and predicting methane emissions. I've just got to go back and look at the data relative to units, methane per unit of milk and stuff like that. But again, I think there's no reason that a Jersey should not be a very excellent animal. The problem, research-wise, we don't have very many in a research setting to get actual measured data. But I think the principles are going to hold the same on the Jersey as the Holstein. The more efficient Jersey, the more productive Jersey is going to be the better model for us. And again, we'll get some data on this particular herd, but that's the best answer I have at this point.
Okay, thanks. So Paula is now having trouble with her mic, so I'm going to read her questions for her. Her first question is from Carlos. Are MUN values similar along the lactation curve? And she's comparing peak with late lactation.
Well, I mean, if we go back to the one slide from Mary Beth Hall, MUN is going to be directly related to the balance of ammonia and carbohydrate in the rumen, and so that's going to be the most important thing. The stage of lactation is not going to be that big of a deal, because if we have a good balance of ammonia carbohydrate at any stage, we're going to be doing quite well. So I think go back to that slide of Mary Beth and look at that. And that one really tells the story. It's ammonia fermentable carbohydrate, and that relationship is what determines MUN. And so I think that's a bigger picture than stage of lactation.
Okay, Paula has a second question from Carlos. What would the response with lowering diet crude protein in growing heifers? Would it be lower gain rates? And then I guess additionally, what happens to lactating cows?
Well, I think, again on a soapbox, I think we ought to forget talking about crude protein, in honesty. I think we should be looking at metabolizable protein. And so again, I think the key is if we have enough metabolizable protein to meet the need of the animal, no matter what the crude protein level is, we're going to be fine. And I mean, if we lower the crude protein in a heifer diet and we get so we're short of MP, then yes, we're going to impact performance in a negative way. As we work with dairy herds, we see quite often that we can lower crude protein significantly. At the same time, we increase MP, and we end up getting more milk at a lower cost. So I hope that shortly we can ignore the word crude protein and look mainly at MP, because I would guess that most of you who run the AMTS program and you look at herds, if you look at the MP available per day versus crude protein across a bunch of herds, you're going to see some interesting things. That in some herds, those high protein levels, they could be short of MP. In other herds, they could be doing very well. Our lowest herd that we are aware of in New York has fed a 14% crude protein ration for about 8 or 9 years now, and they average about almost 42, 44 kilograms of milk. But if you look at the MP, it's about 3,000 grams per day. So even though the crude protein looks really low, MP is very high about what the cows need to make that milk. So I'm hoping we can start talking about MP and forget crude protein, because MP is really the term that we should be using. In your programs, you have the option to do that. The challenge is our dairy producers don't understand MP. They're comfortable with CP. So we still have to balance on MP and talk to them on crude protein until we get them converted over. But there's really, I've looked at a bunch of herds, and there's no correlation between crude protein and milk production, and no correlation between crude protein and the MP in the herds. I can show you herds with low crude protein, high MP, herds with high crude protein, low MP, anything you want to see. So they're not correlated very well. So I tend to look at MP when I do balancing, and then sure we print out the CP for curiosity, but I don't look at it very much other than that.
Okay. So Larry, I have another question from Paula, and this is sort of addressing some of I remember you referenced some research that's being done in Wisconsin. How would you modify rumen populations, inoculating the rumen with specific populations? Question.
That's what they're trying. They're trying to see if they can do that. But I think what they're finding is, probably doesn't surprise many of us, is that rumen ecosystem is pretty dynamic. And if you put in, you try to change the population, the population seems to revert. One of the most interesting studies was done by a person at the U.S. Dairy Forage Research Center a number of years ago, and they took a number of cows. They were all fed the same total mixed ration, and they looked at the microbial population of, like, let's say 10 cows. I'm not sure how many, but 10. Those cows fed the same TMR had 10 different populations in the rumens. Each cow had her own ecosystem, you might say. And so then what they did is they took and they changed those rations totally. They flipped them, like from a high forage to low forage, or low forage to high forage. And they waited about 5 weeks, and guess what? The microbial population of the cow went back to what it was on the previous ration within each cow. So I think the population is going to be pretty resistant. but people are still looking at this because there may be an option sometime. But it looks right now like the population is pretty resistant, and they are able to adapt to these things. That's why the work that Alex Histoff did was with the 3-NOP was very interesting, because he did it over 12 weeks. And at least over 12 weeks, those cows did not adapt. So that's encouraging, because some of the previous work in vitro is done like in a day or two, and they get 70-80% decrease. But then over time, that disappears. So Alex's work is interesting, that here's a specific product that at least over 12 weeks, cows did not adapt, or the ruminants did not adapt. So I don't think this is going to be a big one in the future, but people are still going to keep looking at it, because you never want to say it's not possible, but it looks like a low probability to me.
Okay. So, Larry, I have a question from Jose Hiram Menendez Ramirez. He says, "Hi, doctor. What do you think about long-term supplementation of ionophores, and how would you use them? Dosage, kind of animal, kind of ration, to have better performance in dairy cows? I know that the effect is not consistent."
Right. That's one of the problems, is it's not a consistent effect. And actually, there was a review paper about 1 or 2 years ago that said, short term we know what things like monensin do in the rumen environment. But when they looked at a whole bunch of research papers over a long period of time, about half of them said the effect persisted, and about half of them said the effect did not persist over long term. So actually, in honesty, the ionophore question, short term, yes, it does help. There's still a debate whether long term it helps or not. And again, as you probably know, at least in the U.S., the only claim right now on monensin is for feed efficiency, and I think we do see it used in some herds. It's relatively inexpensive, but there is a question of whether you get a long-term benefit or not, and the research data is mixed at this point.
Okay.
Heifers high forage diets, it has been shown years ago that is a very positive thing, very beneficial.
Okay, thank you. I have a question from Stephen Brooks. First of all, he says he's sorry he missed the first half, and the EPA advises that methane and NO2 have vastly greater greenhouse warming potential over time than CO2. Do greenhouse calculations incorporate not just the burp, but the totality which comes from growing the forage and the corn?
Yeah, I mean, you're right. If you look at the relative effectiveness based on CO2, methane is in the range of 25 times more potent than CO2. Nitrous oxide is in a range of 250 to 300 times. But when they do the calculations for CO2 equivalents, which is what they do, they take those weighting factors into account. And actually, we're involved in a project now looking at whole farm modeling of the whole system, from the cows, the crops, the manure, everything, to look at this. So again, the information I presented today is basically right at the cow side, and when you get to the manure and stuff, that's when you get the N2O, but not at the cow. And so I think there's more data coming on that. But when you talk carbon footprint, which is what people are talking about now, they are using the weighting factors in most of those calculations.
Okay, thank you. I have a question from Carlos in Argentina. What would you expect to happen with methane production when using permeated whey?
Well, I think it's going to be a balance of how have you balanced your fermentable carbohydrate in the rumen versus ammonia. With the whey, you're going to have an opportunity to probably soak up a little bit of more ammonia than some of the other sources, because the whey might become potentially more available a little bit more quicker. So I think it's just back to that that ammonia carbohydrate balance, the very best slide, really. So the whey is going to be one that's probably a little bit more rapid than some others. So you could probably use a little bit more rapid degradable source and soak it up and be okay.
If in your notes there's no point to feed more than 6.5% crude protein, so what is the importance of essential amino acids in metabolizable protein?
Well, I think all of you have probably formulated a fair number of rations. And the way that we get the lower protein rations to work is to get, number one, the right level of MP, and secondly, the right balance of lysine methionine. And that's really how we can make the so-called lower protein rations work, is we get that better amino acid balance by driving microbial protein synthesis better, and then putting together either the right undegradable protein sources or some of the synthetic amino acids to balance lysine methionine. That's how we make these lower protein rations work. You have to have that amino acid balance along with to make that work. So it's MP and that balance of amino acids that make these so-called lower protein rations work.
Okay, unless I get something typed in really quickly, I think that Paula doesn't have any more questions from Argentina, and I don't have any questions in any of my windows. I did have a note from Diana Allen in England, and she said thank you for a great, straightforward presentation, and then went off to bed. So,
terrible.
Yeah.
I know her.
Okay. So I guess if nobody has any more questions to type in really quickly, I just want to thank Dr. Chase again, and he's sitting right next to me, so that's why it's been kind of both easier and harder in some cases. And we will look forward to having you all join us next month, and hope you enjoyed this particular presentation. Thank you, Larry. Thank you, Paula. Thank you in absentia, Marcos and Marcelo. And Paula, hopefully the mic will work next time. All right. Good night, everybody.